Hello everyone, a warm welcome to this course, Mathematics 2. Basically, this course is about linear algebra. Okay, the entire course you will be studying about vectors, vector spaces, matrices, eigenvectors, eigenvalues, inner products, symmetric matrices, all these kind of ideas. These are very crucial in engineering. At this point when you study them, I will talk a little bit about applications, but I may not be able to provide them in great detail, but I can assure you many of the courses that you will see going forward in engineering will use a very strong dose of linear algebra. So make sure you study these ideas very clearly, and some of the concepts should be very clear in your mind. Okay, so let me give you a high level view of why this is important. At this point, you may not have really seen many engineering systems or any system at all, but it's very typical for any system to have inputs and outputs. I've called them variable set 1 and variable set 2, right? And it's also very typical to model the outputs as linear functions of the inputs. So what is this linearity and all? You'll see later, but these linear functions of the inputs are very important. For instance, one simple fact might be, if x1 increases 10%, you may want y1 also to increase 10%, keeping everything else the same, right? Or a corresponding percentage. Okay, maybe 10% may result in 20%, 5% may result in 10%, like that, right? So quite often this linear relationship is very interesting. In fact, even if it is not linear, quite often and for analysis purposes, we'll simply assume it's linear, or in a small parameter range, you assume it's linear and do something. So this linear system assumption is very crucial. So set 2 depends linearly on set 1. So if more precisely, if people express it, they'll assume that there are these coefficients, this aij, right, a11, a12, so on till amn, so that this y1 to ym becomes what is called a linear combination. So you take a11 multiply by x1, so on till a1n multiply by xn. Like that, you make m linear combinations with m different sets of coefficients to the same inputs to get the outputs y1 to n. This is a very common assumption. So this entire course, you can say, is about studying equations like this. Okay, what happens when you have equations like this? What all can you do? What all can you not do, right? How do you find these coefficients given some sets of inputs, outputs? All these kind of very interesting problems are there, which are at the heart of many applications. Okay, so these coefficients are important. They characterize your system. So you may ask, how to find set 1 for desired set 2 given coefficients? The coefficients are given. I want a particular output, y1 to ym. How do I set the input? Right? So given the inputs, finding the output given the coefficients might be very easy, but the other way around might be difficult. You may also have other set of properties. I may want a desired relationship between input and output. How do I design the coefficients? That's also very important. Okay, that's like a system design problem. System is given, for what input will I get what output? That is like analysis type problem. But system itself is not given. I need for this input, I want that output. How do I design a system? What kind of systems are possible? So these kind of questions permeate engineering and science. A lot of scientific areas, engineering areas depend on such system analysis. And you can see very easily linear combinations, equations, linear equations of this form are at the heart of it. So we'll study essentially this, okay? But we may not be so applied all the time. So you'll see we'll be studying a lot of theoretical ideas around it. Okay, so like I said, so many applications are there from all sorts of areas. It's not wrong to say that every single area and sub area of engineering and science uses linear algebra. Okay, it's not at all an exaggeration. Okay, so make sure you understand the core ideas here, and you'll see if at all you end up in studying electrical circuits, mechanical systems, population numbers, how population grows, and how, for instance, COVID-19 pandemic grows, all these kind of things, and flow of physical quantities, information. The World Wide Web is like people model it using linear algebra. Okay, so a lot of things are there. Control systems, particular uses, a lot of linear algebra. So applications abound. We won't have too much time to go into specific details of applications, but as you study more engineering, I'm sure you'll come across matrices dominating every single application area. Okay, so what exactly will we study in this class? We'll study linear algebra, like I said. We'll begin with vectors, matrices, linear combinations, linear equations and their solutions, vector spaces, subspaces, spaces, dimension. So this will be the first part of the course, first 4 weeks, so to speak. The next 4 weeks, we will study about eigenvalues, eigenvectors. So eigenvalues, eigenvectors are very important and crucial in studying what are called operators, and basically square matrices in some sense, and we'll spend quite a bit of time to make sure that we understand those ideas very clearly. And then we'll move on to this notion of inner product, magnitude, distance between vectors. These are becoming very, very important. And finally, we'll study about transpose, adjoint, least squares, and properties which are symmetry and all of those kind of properties. Okay. So this will be the last 4 weeks or so of the class. So roughly 4 weeks of pure vector spaces, linear equation solutions, 4 weeks of eigenvalues, eigenvectors, and 4 weeks of inner product, magnitude, inner product spaces as they are called, symmetry, all of those things. So those are also very, very important. In fact, in the new age of data science and data analytics, matrices will become so much more important, right? So applications for these topics abound, and they are so many in number. Okay. So one of the approaches we'll do in this class is to highlight many of the concepts in R2 first, in the two-dimensional real plane. The reason why we do it is the two-dimensional real plane, a lot of things can be visualized with lines and what happens to lines and scaling and rotation. Many, many things are easy to visualize. You can draw pictures. So we'll do a lot of study with two-dimensional plane, and then we will extend it to the n-dimensional version. So quite often you may find it slightly repetitive, as in some of the things I develop in 2 dimension, I will again develop it again in n dimensions, but I will try to go a little faster when we do the n-dimensional stuff, but still some of the ideas will extend almost directly, but some of the proofs and other things will be genuinely different. So to help with the visualization, we'll stick to this approach in this class, 2 dimension, then leading to higher dimension. Okay. So the emphasis largely will be on methods and their derivations. It's an engineering course in some sense, right? It's a mathematics course, but in an engineering topic. So we will focus on methods. How do people think of, what is the idea behind eigenvalues? What are the concept behind that? And how does one write it down for small cases? Things like that we'll point you towards computer packages that can do this and all of that. So it's definitely an applied version of the course, not a pure theoretical version. But we'll also focus a little bit on this linear algebraic reasoning. How do you think of subspaces? How do you think of vectors, vector spaces, eigenvalues? What is the way to think about them conceptually, and how to apply them in reasoning problems, right? So that's also something we'll do. We'll do proofs. Most of the statements I make in this class will be proved in class, but this course is not a pure math course, so we will not expect proofs from you in the exams and all that. Okay, so proofs are meant for improving your understanding, getting deeper understanding on the topics. A lot of deep understanding comes from understanding the proofs. So we will do proofs, but we won't expect that you repeat the proofs in the exams. And those kind of questions will not be a priority in this course, but nevertheless I would urge you to make sure you look at the proofs very, very closely. Okay, so that's the end of the introduction. I hope you got a sense of what we are going to do in this class, and like I mentioned, linear algebra is so important in today's world, particularly in today's data driven world. So welcome to this course. I hope you have a great time learning in it. Thank you very much.